In Unit 6, we're going to explore quadrilaterals, other polygons. Our focus is going to be on quadrilaterals generally, but today we're going to kind of dig deep into other polynomials. We're going to learn about the Polygon angle sum theorem. Apologies for the Christmas sweater. It is December, and I'm making this for January, and so enjoy the ornaments. As we jump into this unit, we want to make sure that we can think about polygons, think about what we know from our elementary and middle days about polygons, naming them by their number of sides or number of angles. It should be the same number, and just some fun facts about polygons. And so this will be sort of a general lesson, introducing polygons, exploring polygons, their nature, their relationships of sides and angles. And then we'll sort of narrow our focus to quadrilaterals for really the remainder of our unit together. And so our goal is to make sure that we can remember the vocabulary associated with polygons based on their number of sides. And so we know that a three-sided polygon is a triangle, a four-sided polygon is a quadrilateral, etc., etc. You should be familiar with all of these names: pentagon, hexagon, octagon. But then after this vocabulary might be, it shouldn't be new, but it's probably just less familiar. So a 9-sided polygon we call a nonagon, 10-sided is a decagon, and a 12-sided polygon is a dodecagon. All right, so those may feel like they're new terms, and that's okay. You'll notice that we skipped 7, which is a heptagon. We skipped 11, which is onagon, but we don't need to know those terms for this unit. I do expect that you know this vocabulary. So if I'm talking about a hexagon, I expect you to know that the number of sides, n, is 6, and the number of angles in that hexagon is 6. I hope that you can connect these numbers with these names. That's really the big deal. If a figure has more than 12 sides, or even if it's 7 or 11 and we don't have the vocabulary term expected here, then we're just going to call it an n-gon. All right, so if it's a 7-sided polygon, we can call it a 7-gon. If it's an 18-sided polygon, we'll call it an 18-gon. And so it's kind of a weird way to write that, but that way we don't have to learn or memorize additional vocabulary. So the other key vocabulary is convex versus concave. When we're talking about polygons, our general picture in our brain is a convex polygon. But we do understand that concave polygons exist, and these are defined as polygons that look like they have a little cave, right? That's how you learned about it in elementary school. The formal definition is that at least one of the diagonals has points outside of the polygon. So let's talk about what diagonals are. Diagonals are segments that connect non-adjacent vertices. All right, segments that connect adjacent vertices are just the sides, right? And so these are diagonals from this vertex, but I could also draw diagonals from that vertex. I can draw diagonals from this vertex, and I can draw diagonals from that vertex. And so all of these diagonals are inside of the polygon. This is convex. All right, if I were to draw diagonals in this polygon, obviously, okay, those are inside, but then this one kind of goes outside. This one's inside, cool. What about from here? This one is inside, this is inside, this is, ooh, it gets a little close. Oh, this one comes outside. So since we have parts of those diagonals going outside of the polygon, this is concave. Now this is sort of a formal high school geometry definition for convex versus concave. Frankly, I don't care which way you understand it. If you just take the elementary approach and you're like, well, this is concave because the bear goes in the cave, that's totally fine with me. I just care that you can distinguish those terms from one another. We want to explore the sum of the measures of the angles in these polygons, all right? And so what we want to do is, as we are exploring the number of sides, which again is equal to the number of angles. In a triangle, there are 3 sides, right? But the name triangle means that there's 3 angles, all right? Quadrilateral, 4 sides, all right? But a quadrilateral also has 4 angles. So the number of sides in each of these polygons is the same as the number of angles in those polygons, right? Make that note. It's not written up here, but you should write that down. That the number of sides is the same as the number of angles in polygons. So what we want to do is find out what is the sum of the measures of these angles in a quadrilateral and a pentagon, et cetera, et cetera, et cetera. And so we know that with a triangle, the sum of the measures of the angles in a triangle is 180 degrees. We proved that in back in lesson 2-3 in first semester. And we showed that the sum of the measures of the angles we used parallel lines and another exploration in there to show that the sum of the measures of the angles in a triangle is 180 degrees. And so what we kind of want to do is we want to break this up into non-overlapping triangles. All right? If I can draw a diagonal in here, all right, from any vertex, but you'll notice that I have 2 triangles, right? If I draw it from here to the other I've got two triangles. If I draw it from here to the other, I've got two triangles. All right, and these triangles don't overlap. And the angles for this triangle, 1, 2, and 3, and then the angles in this triangle with 1, 2, and 3, these don't overlap at all. But this triangle has 180 degrees, and this triangle has 180 degrees. And so if I were to add those two together, I would get a total of 360 degrees because there's two triangles, 2 times 180. With a pentagon, the same thing would be true. If I pick one vertex, it doesn't matter which one, but if I draw in the diagonals from just one vertex, these triangles don't overlap. How many triangles are there? Well, there's 1, 2, 3 triangles. So we could take 3 times 180, and that would tell me the sum of the measures of the angles in this pentagon. All right, so we know that in every pentagon, the sum of the measures of the angles is 540. It's 3 triangles. The sum of the measures of the angles in a quadrilateral, every quadrilateral, will be 2 triangles, 360 degrees, etc., etc., etc. So what we've determined here is no matter how I draw those diagonals, I will always have this many triangles. Now, how is this number of triangles related to that number? How is this number of triangles related to that number of sides? How is this number of triangles related to that number of sides? Hopefully you can deduce that what we have here is the number of sides minus 2. The number of sides minus 2. The number of sides minus 2. That's how many triangles we have. So we're going to take n minus 2, that number of sides minus 2, and multiply by 180. You can write it like this, or you can write it like that. Either way that you write that is fine with me. I think it's, if you write it like this, you're probably going to distribute that 180, which is not what I want you to do. It'd be easier to subtract it and then take that number and multiply by 180, maybe a little bit easier. All right, so the number of sides minus 2 times 180 is going to give you the total number of degrees when you add up all of the interior angles in the polygon. This is the polygon angle sum theorem. And so there's a corollary there. If we are dealing with a regular polygon, now again, regular polygon, all the sides are congruent, all the angles are congruent, so we're talking about a square, we're talking about an equilateral triangle, we are talking about a regular pentagon like you see in Washington, D.C. If all the sides are congruent and all the angles are congruent, then what we can do with that information is take the total number of degrees in the polygon and divide it by the number of sides, which is the same as the number of angles, right? So if there's 4 sides, that means there's 4 angles. If we have 360 degrees, and we divide 360 by 4 angles, then that means that each one of them has to be 90 degrees, and we know that that's true in a square. In an equilateral triangle, we showed that we had 180 degrees, we divided by 3, each of the angles is 60 degrees. Now this pattern continues with a pentagon, a hexagon, etc., 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 where we could take the total number of degrees and divide by 5, or divide by 6, or divide by 7, or divide by 8. And it would give us the measure of each of those angles in a regular pentagon, hexagon, heptagon, octagon. All right? So let's do a little bit of work. Given the number of sides, find the sum of the angles in the polygon. It doesn't say that it's a regular polygon. I don't know the measure of each angle per se, but what is the interior angle sum in a hexagon? So we have to understand that this means that n is equal to 6. Pause the video if needed, if you need to write this stuff down. And what we're going to do is we're going to use our formula, which is n minus 2 times 180, or 180 times n minus 2. It doesn't matter how you do it. You're going to get the same thing, all right? So the total number of degrees is going to be found by taking 4 times 180. And if we take 4 times 180, we are going to get 720. This is the sum of the measures of the angles in a hexagon. Every hexagon, all right? It doesn't matter if it's a perfect honeycomb hexagon, you know, 2 isosceles trapezoids stacked upon each other, all right? It doesn't have to be perfect like that. It could be sort of wonky, right? All right? And all 6 of these, if we added up all 6 of the angles, it would add up to 720 degrees, regardless of the situation. I want for you to try this, all right? Use a calculator. But you get to try that for your full credit. What's the interior angle sum of a 17-gon? So in this case, n is equal to what? Hopefully you can do this formula work here. All right, but let's think about it in reverse. So reverse is a little interesting. Reverse is, if we know the angle sum, what does that mean for the number of sides? So how many sides does a convex n-gon have if the sum of the interior angles is 540 degrees? So this is the total, all right? But we don't know what n is. N is our variable. This is what we're trying to find. We're trying to solve for n. So here we get to use some algebra 1 skills. We know that n minus 2 times 180 is going to give us our total. We have an equation that we can solve. And so we get to do algebra 1 to solve an equation. Can you do the algebra 1? Pause the video and see if you can do it. I'm going to divide both sides by 180. And I'm going to add 2 to both sides. That's going to tell me the sum of the measures of the, I'm sorry, not the sum of the measures. We know the sum of the measures. This is going to tell me the number of sides. So what I want for you to be able to do is, if I give you the total, can you find out how many sides this is? Now, Mr. Hibbett, when you told me to pause the video and I did, so I did it a little bit differently. I distributed the 180, but I still got the same answer. Yes, absolutely. You should do that. You should get 180n is equal to 900, and when you divide that, you're going to get 5. All right, it works itself out. So either way you do that is totally fine. If you distributed the 180 and then added 360 and then you just did an extra step of work, it's fine to do extra work as long as you realize that you're doing extra work, because we're not thinking through the quickest way to approach that. This one's a little bit tricky, and I want for you to try this. I will set up the equation for you though. How many sides does a regular n-gon have? Ooh, regular n-gon. So they're all the same measure if one of the interior angles is 120 degrees. So that means that we have a total 180 times n minus 2 divided by n, all right, same variable, is equal to 120. I would like for you to solve that equation using Algebra 1, Chapter 2. All right, if you can solve that equation using Algebra 1, Chapter 2, then you're in good shape. If not, I will answer it in class. Go ahead and give that a shot to the best of your ability. Pause the video for as long as you need to. All right. Now, we learned about the triangle angle sum theorem. We learned about the triangle exterior angle theorem. Now we're going to generalize, just like we generalized the polygon angle theorem for all polygons, we're going to generalize the polygon exterior angle theorem. And there's kind of some fun facts here that we want to make sure. So an exterior angle is when you extend one of the sides at a vertex, all right? So here we have an exterior angle that is adjacent to an interior angle. This is interior, this one is exterior. All right, and there is one that we could draw. We could actually draw 2 at each angle, but these usually go in terms of having one exterior angle is usually where the theorem comes from. We're just kind of focus on one extension at each vertex. So again, an exterior angle is formed when you extend one of the sides from a polygon, but then you keep the other. All right, so we're talking about this angle formed right there. All right, this is your exterior angle right here. That's the exterior angle. This is interior because it's inside. This is exterior because it's outside. Over here, if I were to extend it this way, this is not exterior. That's not, I know it's on the outside, but it doesn't fit the definition. It's formed on 2 extensions, not an extension and a side. So we have to read that definition and understand, obviously this is where your English language comes into play. That's why you still take ELA classes, so you can read sentences and understand what they say. All right, hopefully that explanation was helpful. If it doesn't, make a question mark and ask about it in class. So what the big deal is here is that this angle and that angle are a linear pair, right? They are supplementary angles. Together they make a straight angle. So we know that this angle plus that angle makes 180. That's kind of the big deal that we want to remember from Chapter 2, Lesson 3. We're exploring it again here in Chapter 6, Section 1. But here's what we know. In every polygon, if you were to add up all of the exterior angles in any polygon, they will add up to 360 degrees. All right? Regardless of whether or not it is a regular polygon. It doesn't have to be a square. It doesn't have to be an equilateral triangle. It doesn't have to be a regular hexagon. This is still true, that the sum of the measures of the exterior angles is and will always be 360 degrees. All right? By corollary, if all of the interior angles are congruent in a regular polygon, then that means that the exterior angle or each exterior angle in that regular polygon will be that total divided by how many there are, divided by n. There are n sides in an n-gon. There are n angles in an n-gon. There are n interior angles in an n-gon. There are n vertices in an n-gon, and there are n exterior angles in an n-gon, one in each vertex. All right, so keep that in mind while we do this next line of thinking. So here, we are going to have 2 situations. Draw this picture, pause the video as needed. We have exterior angle, exterior angle, exterior angle, and this one's not labeled, but we know that it's going to be 90, right? If these are perpendicular, that means that these are two right angles, which means that they're both measuring 90 degrees. And so they don't tell us this, but we know that it's true, all right? They don't tell us this, but we know that it's true because we are thinking people. But what we have is we're going to add up all the angles. The sum of the measures of the angles is going to equal 360. So we're going to create an equation that says 2x, I'm trying to find room, sorry guys, 2x minus 24 and x plus 14 and x, and we know that this is 90. These are all going to add up to equal 360 degrees. So we have this angle and this angle and that angle and that angle. Those four things are together going to add up to 360 because the sum of the measures of the exterior angles in a polygon is, say it with me, 360, good job. Combine like terms, all right? So we have 2, 3, 4 x's. Negative 24 and 14 makes negative 10. Negative 10 and 90 makes 80. Oh, I don't have a calculator. Oh, this is going to be rough. We subtract, we get 280. Oh, this is, I can divide. X is equal to 70. All right, that worked out pretty well. So what we want to be able to do is create an equation where the sum of the measures is equal to that total. All right? Now, these questions may be phrased a little bit differently in our classwork. We might have where these angle measures are inside. And we know that the interior angles have to add up to n minus 2 times 180. So it would be a very similar situation where we still create the equation and then we do our work to find out what the value of the variable is. This one you're going to get a weird answer. Don't freak out because you get a weird answer. Use a calculator if you can't handle the division. If you want to answer it with a decimal approximation, I would avoid that. I would answer it as either a mixed number, probably a mixed number instead of an improper fraction, but kind of your call on this. This is a regular polygon. I want for you to try this based on this relationship that we know here, and especially the corollary. You need the corollary to answer this. Use the corollary. Use the corollary to Theorem 6.2. All right, use that. You're going to use this corollary from Theorem 6.2. All right, you're going to try this one. I'm not going to write out the formula for you on that. You're going to do your best. You are going to get a decimal answer, and that's okay. See if you can round that. I'm sorry, don't round that. Just go ahead and answer it as a mixed number. That's probably the best way to do it. And that's the end. That hopefully you are able to find the sums of the measures of the exterior angles and the interior angles of polygons.